Today we're going to cover state space models. In the last lecture, we were deriving simulation diagrams, and the objective of these simulation diagrams was to expose some of the internal variables in a system so that we would have access to them, as opposed to just having a transfer function where only the input and the output are available. These internal states are typically required in order to predict the future behavior of a system. Let's, for example, assume that we have a muscle that has been stretched and released. It's been stretched by applying a force to it. If we want to predict the displacement or the future position of that muscle, we'll need to know two things. We need to know the current position, and you need to know the current speed, because both will affect the future behavior. So these are internal variables that we are not only exposing when we create a simulation diagram, but we also need them in order to predict the future behavior of the system. And a state space model is a set of equations that will describe the future behavior of the system when these specific states, internal states, are available. We're going to derive our equations as a function of these states that are needed to predict the future behavior of a system. For example, if we consider the capillary network that we studied before, and you want to predict future blood flow, we'll need to know, in addition, of course, to the inputs to that system, we need to know at which state that system currently is. If there is any element that can store energy in that system, we'll need to know what is the current state of those energy storage elements to predict the future behavior. In that case, that would be the fluid inertia, and would be how much fluid is stored in the caterpillar in the form of a potential energy. These are two internal variables then that you need to consider in order to predict the future state of that system. So now the idea in the state space again is to identify these specific elements in the system that are storing energy that are required in order to predict the future behavior of the system, and then write equations as a function of them. There is one big advantage of this approach compared to transfer function, and that is the fact that we can now reduce the order of all differential equations that describe the behavior of these systems to a first order equation. So if you have a system, for example, the muscle system would be a second order transfer function, we can now write that system as a system of two first order equations. If you consider the one that we had in the assignment, when you had two masses inside of a casing, that would result, if you did it right, you would get a fourth order transfer function for the input output relation. That's a fourth order transfer function that we can now write as a set of four first order differential equations, which makes the process easier to analyze and easier to simulate later. So in this lecture, that's what we're going to study. Okay, so this can be a bit complicated. So let me know if there's any questions. Yep.
I just had a question that's not related to the lecture, but related to the course.
Yeah.
So are there, for labs next week, because of Thanksgiving, is it going to go as normal for the Friday section, or?
So we are going to, so Monday is a holiday. So what they're going to do for that lab is that only the lab report is required. So they're going to be, for both sections, there will be during the lab period. And then the Friday section, the TAs will be available to answer questions. But,
okay.
You're not required to attend. We're going to do lab 5 virtually. The deliverable will simply be a report, but the TAs will still be available on Friday to answer questions if you have any. So both sections can attend Friday meeting if you have questions. If not, then just submit the report, and you're only want to evaluate the report for this one.
I understand. Thank you.
Okay. Yeah. So the objective here is to represent differential equations using matrices. We're going to now lower the degree of these differential equations, obtain a state variable model for a system, and understand the role of these variables in how they contribute, how they can predict the future behavior of any system. So my picture here is not showing very well, but a typical example where this type of analysis is used in aerospace engineering. If you want to know the future orientation of the space station given a control action, what do we need to know? We need to know how it's currently moving, where it is, and of course the input to that system. But the input by itself is not sufficient. We need to know the current state of the system in order to predict its future behavior. So which are these variables that are needed in order to predict the future behavior? We need to identify them and then write the equation as a function of them. Here we have, back to the surgical robotic example, a robot arm. Again, this is showing better in your picture. If you want to give a position command to a biomedical robot, what do we need to know in order to predict where it goes? Or if in these differential equations, which elements specifically are contributing to oscillations in the robot arm movement, which ones are contributing to an exponential decay of these oscillations? If we can identify them, we can control the robot better and potentially avoid oscillations. In some examples, if you think about eye surgery, for example, we don't want to go beyond a certain target. So if there are oscillations, we may puncture the eye, for example. So here, it would be preferable to reach a given position is lower, but using an exponential curve rather than faster with some oscillations, because anything that exceeds this final value here can potentially be harmful. So which elements in the transfer function are responsible for this behavior? We can identify them using a state space representation. And which ones influence the steady state? That's another question. We can discern these two parts and then study them separately. So let's now formally define what we want, what I mean by a state of a system. So the state of a system is the minimum set of variables that provides the future state and output of the system, the minimum set of variables that are provided the future state of the system and output of the system for a given input. So the system has an input, we pass that through the differential equations, and we get the future states. So to calculate future states, we will need to know the current states, we need to know the input of that system, and we can define an output. An output could be one of these states. For example, the mass spring damper system, two states are required, position and speed. We'll see why later. If you want to predict the future states, we need the current states, current position, current speed. Which is the output? Which one is the output? Well, we can define them as either, or we can define the output as being something else, but the output will depend on the state. It's not necessarily a state, but it could be one state, it could be something else. That will be a function of these states. And you're going to define these state variables in a vector. We're going to gather all of them in a vector. We're going to represent here as x of t. x1 is one state, x2 is one state, and xn is another state. So for a differential equation that has a order of n, we'll have n state variables to represent it. Examples are position, velocity, current, voltage, fluid flow, potential energy in fluid, etc. And if you look closely here, there is a trend in these variables. And the trend is that each of these elements are capable of storing energy in the system. In a mass spring damper system, we store energy in the form of potential energy, and that depends on the position of the mass. We also store energy in the form of kinetic energy, which depends on the speed of the mass. In an electrical circuit, we store energy in a capacitor in the form of the electrical field, which depends on the voltage in that capacitor. And in the inductor, in the form of a magnetic field, which depends on the current on that inductor. So a first good approximation in order to define our state variables is to first look at which elements in the system can store energy, and then which variables are directly related to the energy storage, and then find them as state variables. So we're going to see this choice a little bit better in the next lecture. So today we're going to just cover the basics and then expand it next. Let's consider here the mass spring damper system. We use this to model many things so far, a biomechanical model of the leg. If you haven't taken, everybody took lab 4, right? Yeah. So a biomechanical model of the leg, the accelerometer that we used in the assignment, a muscle. So this can represent a variety of different systems. If the input to this system is u of t, that is a force, and the output is y of t, let's call that a displacement. What variables do we need to know to predict the new state of the system given a initial force? Now we need two things. We need the current position, and we need the speed. Why? Because those are the two that are directly related to energy storage in the system. The position will regulate how much energy we can store in the spring in the form of potential energy. 1/2 of x squared times k. The speed of the system, which is the derivative of position, will regulate how much kinetic energy we can store in the system, 1/2 of mv squared. So these are two elements storing energy, so we can define them as state variables. So now our state vector that will gather all this information about the elements storing energy here, let's call that x of t, and it has two elements, x1 and x2. x1, we can call that the displacement. So x1 is y of t. And x2, we need the speed. So the speed as a function of y of t is simply y dot of t. Y dot of t. Okay. Which is the same as x1 dot of t. Right, so two states are sufficient for the system. It would be a second order differential equation if you model it, or a set of two differential equations. One differential equation is already here. We have x1 dot of t equals to x2 dot. This is the first differential equation. Where's the second one? Well, the second one we'll get by establishing now a model for y of t, and then that's how we're going to get x1. So let's do that. So here we have the two equations again. X1 is the position, x2 is the derivative of position, that is the speed. And if we write the differential equation describing the dynamic of this system, we get the third equation. We went through that a couple times, so I'm not going to go over that again. Let's just now rewrite this equation as a function of our states. And when you rewrite the equations as a function of our states, here's the rule. We always want to, we are trying to eliminate derivatives as much as we can. So let's use the variables that have the lowest derivative whenever possible. For example, m dy double dot, sorry, my double dot. Well, how could we write that? We could write this as m x1 double dot, because x1 is y. Or we could write this as m y x2 dot. Which is the same as taking the derivative of both sides of this equation here. If x2 is y dot, then x2 dot is y double dot. So two ways to write the equation. If we go with the first method, x m1 dot, we haven't really done anything because we still have a second order differential equation. Now, if we go with the second one, we see that we lowered the degree of the equation by 1. Use the lowest available derivative. So now let's write this equation using this method. So how would that look like? M dy m y double dot is the same as m x2 dot. Is this one fine? Is this clear?
Yes.
Yeah, right, which is, so x2 dot is d squared y dt squared plus b times what now? We have, what can we write there? We could write x1 dot or
x2.
x2. So x2. Of course, these are all functions of time. Just writing x2 to make it easier. Plus k times
x1.
x1, very good, equals to q of t. So this is one of the differential equations. And the other differential equation we get from here. If x2 equals to y dot, then this is the same as x1 dot. So the second equation is x1 dot equals to x2. I have the two equations that will describe the same behavior. Right. Okay. Our objective is to highlight how these states change. And when you talk about change, we are talking about their derivatives. So the objective is always to have equations that explicitly give the derivative of the state. Why the derivative? Because that's the rate of change. That's what we are interested in. So if we take this equation and isolate for x2 dot, we have u of t minus bx2 minus kx1 all times 1 over n. So here is one equation for the derivative of one of the states, basically how the speed is changing over time. And the which is the acceleration, and then the other one is how the position changes over time. With these two equations, we can now reconstruct the behavior of the system, given an input, and given now the initial conditions of the system, given how the system, or the current state of the system. That's why we call them state variables. Let's look at this system. Now it's an electrical system, and what do you have here? We have a current source on the left. We have a capacitor, an inductor, and a resistor. Let's define the state variables for this system. So I briefly mentioned that a good choice would be to look at elements that can store energy. Which elements here can store energy?
The capacitor and the inductor.
Exactly. So the inductor and the capacitor. The inductor will store energy in the form of an electrical field. So what is directly related to that is the current through the inductor. Let's call that IL. And the capacitor is also storing energy in the form of a electrical field. And then we can call that a capacitor voltage, VC. Right? The energy is related to the capacitor voltage, not current. Now there could be energy stored in a capacitor even though the current is 0. Right? So it doesn't make sense to have IC as the storage element. It needs to be VC. Okay. All right. So now I have these two equations, these two variables, and you can create our state vector here as x1, x2, and then assign x1 IL and x2 VC, or vice versa. We can choose whatever we want. Let me just cheat here and look at what I did. Okay, so V1 is VC, and x1 is VC, and x2 is IL. So these are now the states of the system. And what are we looking for again? We are looking for equations that will give the derivative of x1 and they will give the derivative of x2, or how these are changing over time. And they will be a function of the input current and be a function of the elements in the circuit. And we can define our output as whatever we want in the system. We could define the output as VCIL or IC, the current through the capacitor, but we chose here to define the output as R times IL, or the resistor. Now let's rewrite the equation of motion for the equation of motion, the governing equations for this circuit based on the states we just established. Here are our states, and let's see how we can do that. So now we have to first find the equations in a, excuse me, the equations in a traditional way, and then replace the equations with the state variables. So we can start to analyze the circuit from this point here. So from this point, you have the current U of t going in, and you have IL going through the inductor, and we have a current going down the capacitor, that's IL. So we can write that as U of t equals to IL plus IC. IC is not one of our states, so we need to get rid of it. But VC is one of our states. So what is the current through the capacitor? Isn't that integral, isn't that C times dVc dt? Notice now that we rewrite the equation as a function of the input. That needs to be there, we can't change it, but everything else in this equation are states. IL is a state, dVc dt is also a state. Okay, so that's where this first equation comes in. What else can we write here? Well, we can take this loop here, and this loop we can write another equation there. If we do Kirchhoff's law here, we have L times DIL dt. IL is a state, so it can stay there, plus RIL, that's also a state, can stay there, plus the voltage through the capacitor, or minus the voltage through the capacitor because you're going upwards against the current. So what does that give? That's simply VC, right? Or the derivative 1 over C integral of IL minus IC, or whatever, how we define the current there. Doesn't matter in this case because the voltage itself is a state. So you can simply write that equals to VC and equate this to 0. Okay? So that's where this second equation came from. And then the third equation is simply the output. Now we also want the output to be related to our states. The output is V0, which can be simply written as L times the current through the inductor, which is a state. Okay. Now let's take our equations and rewrite them as a function of our state. So here is the first one. How do we rewrite this equation as a function of the states? So C is a constant, that doesn't change. dVc dt, what is that in terms of these states? Remember that Vc is x1. So what is dVc dt?
X1 dot.
X1 dot, exactly, X1 dot equals to U of t. That's a current, the input doesn't change, minus IL, which is simply x2 of t.
Sorry, can I ask a question?
Yeah.
Do we need to write x1 dot of t instead
Yes,
of just?
Yes, I will omit now the t for the variables just to save some time.
Oh, okay, thank you.
Okay. Second equation, how does that look like in terms of state variables? L times DIL dt, that would be x2 dots, right? x2 is IL, so DIL dt is x2 dot. Equals to negative R x2 plus Vc, which is x1. Is this one clear? Yeah, no, perhaps? No good here?
Professor,
Yes.
could you please?
Yeah.
Sorry. Could you please explain again why the equation on the right side is minus Vc?
Yeah, so Vc has a current defined as going down, so this means that this is positive, this is negative. And everything else, if you follow the current through it, goes the other way.
Oh, okay, got it. Thank you.
Right, so when you go up through the capacitor, we have negative voltage. And the last equation is V out, V0 of t equals to R times IL, which is simply x2. So here we have a set of 3 equations that describe the behavior of the system. Notice that if we had a transfer function between input and output, this would be a second order differential equation. But here we have 2 first order differential equations and the additional equation for the output. Okay, so now all I did here was to isolate, so for x1 dot and x2 dot, so you see to just divide both sides of the equation by C and L respectively. And here is the result of that. And these are the equations we just came up with. Now, here comes the definition for the state space model in a matrix format. We want to write these equations as x dot equals to ax plus bu. What does this mean? We want to know how the states change over time. That's x dot, the derivative of the state vector, which is a function of this current states times a matrix A, a matrix of constants, plus a matrix of constants times the inputs of the system. So let's see what this equation is saying again. It's saying that the future states or the variation of the states depends on the current states, depends on the input, and each of them are weighted by a matrix of constants that we are going to take from the equations. So our goal when you deal with the state space is always to write the system in this format. This will give the rate of change of the states as a function of the current states, as a function of the future states. That's precisely what we intended to do from the very beginning. So let's see how we do that. So in this case here, we have two states. If you have two states, then the state vector is a 2 by 1, like that. This is also 2 by 1. This is the same. And then the matrix A will be always a square matrix. In this case, 2 by 2. So how do we now rearrange these equations in terms of the representation we want? You see here, this is A, this is X, this would be B, and that is U. So if you start with A, and let's look for the expression for X1. X1 is the first line in the equation, in the matrix, and it's that one. So we see that there is no X1 dot does not depend on X1. So the first element here is 0. X1 dot depends on X2, and the constant is 1 over C. X1 dot does depend on the input U of t, and the factor there is 1 over C. If we now multiply this out, we go back to the first equation we had. Very good here?
Yes.
Yeah. Okay. Now, what is the expression for X2 dot? What goes in the first element?
1 over L and 0.
1 over L. That's for X1. Now notice there is also X2.
Oh, okay. So it's
Right.
minus R over L.
Right. Minus R over L times X2. And what goes in the matrix U?
0.
B 0. Right. Okay. Notice again that if we multiply the second row or the second line of the equation here, this multiplies that, and multiply this, 0 multiplies U, and we go back to X2 dot, which is the second equation. Right. Are there any questions?
Sorry, can we go to the last slide quickly? Just 1 second.
Any other questions?
Thank
So
you.
what was the point of getting an equation for VO?
Yeah, so we're gonna get to that right now. So we only for now got an equation for the first part of our job, because here we have simply the variation of the state as a function of the current state and output. We haven't established a model for the output yet. So that's the next step. So this is a step 1 out of 2. Before we go to step 2, are there any further questions here? No? Okay. So now we want to write a second equation, as this second equation is related to the output. And this is the format for the second equation. Y of t is our output, will always be the output. And we say that the output depends on the current states, depends on the input, and is weighted with two matrices, C and D. So now let's do the same. What did you define as our output? Our output was y of t equals to L times R, which a function of our states is simply x2 times R. You see that there is no u in there. So this entire part here is 0. Now it would be basically 0, 0, x1, x2. And then the first part, we see that it depends on x2. The coefficient here would be 0r, and this is times x of t, so times x1, x2, if we write it fully, plus that. And this is now the second set of equation that will give the input, the output. So here is the full state space model for this circuit. Two sets of equations, and this is the definition for all state space models that we are going to go to use from now on. Only two equations. How big these matrices are? Well, it depends on the order of the system. So if you had a third order differential equation, then it would have three states. Matrix A would be a 3 by 3, matrix B would be a 1 by 3, and so on. The more states we have, the bigger matrix A and C will become, and they will always, for matrix A, is always a square matrix. And that's pretty much it. That's the idea.
I'm sorry, for the second term, there shouldn't be, it'd be 0 u of t.
0, yes, that is correct.
Okay, awesome.
Thank you. So this is times 0. Thanks to be. Let's write this properly to avoid confusion. So y of t equals to 0r x1, x2 plus 0, 0 u of t. Any other questions?
All right, how did we know that u of t is 0?
U of t is not 0. U of t is just not included in the equation for the output. So if you look at the equation for the output here, this is plus 0 u of t.
Okay, I'm sorry, where did the output equation come from? Was that written above?
Now the equation, the output equation was established by defining the output as being V0. So y of t equals to V0, which is the same as RIL, which is the same as R times X2.
Okay, thank you.
Okay. We arbitrarily chose that the output to be V0. Could have been anything. If the output was, let's say, the current through the inductor, then the output would simply be X2. If it was simply the voltage across the capacitor, then it would be X1. And then this matrix here would change. Okay? Any other questions?
Sorry, can you quickly just go through the first line again?
Which line?
X of t equals x1 of t times x2 of t to the power of tau. If I'm not.
No, so this is different. This is just a vector that has been gathered here with, it's not times, is a vector. So first element in the vector is x1, second element in the vector is x2. The t is the transpose, is just to arrange it in a nicer way to show. This is that, x1, x2. And if you transpose it, then you put that in a line, right? It's just, is there just to save some space to transpose.
Oh, got it. Thank you.
Okay. All right. So let's do a recap here, and then you're going to do examples. So the state space standard form will always be like this. We will have a state vector within states that it will depend how many, it depends on the system. It depends on the order of the differential equation. If you have a fourth order differential equation, then you're writing the system with 4 first order equations, n equals to 4. We have a matrix A that is always squared, it's n by n. This is the state vector itself. So the first one is the derivative, this is the state, and then you have the input vector here. It depends on how many inputs we have. It depends on, of course, how many states we have. So m would be the number of inputs. We are going to stick to 1 only. So this will always be a 1 by n. And then the last one is the input. Depends on how many inputs we have. Once again, just 1 input. So that would just be 1/3. And then the second equation will relate the output with the input with the states and the input of the system. So here are the steps for analysis, one by one. Derive the differential equation, same way I've been doing it. Derive the states variables or define them. Then rewrite the equations as a function of the state variables. Arrange the equations in terms of the derivative of x, right? And highlight this term, write everything as a function of them. And then simply form the matrices for both the state variables and outputs. We're going to do some examples and follow these steps. Okay? Yeah. So let's do this one. Let's do exercise 1. We have a system here with 2 masses connected by springs and dampers. We have 2 inputs, sorry, 1 input, that's U of t, that's the force applied to mass m1. And we have 2 outputs. No, we have 1 output that we define to be P of t, that is the position of this mass. And then the position of the other mass is Q of t. This one we chose to be the output as well. Now we want to calculate the state space variable representation for this system. First things first, let's derive the differential equations for this. How will we do that? Well, we can isolate each mass, find the equations of motion, find the free body diagram, sum all forces, and so on. So at this point in the game, I think it's fair to assume that you all know how to do it, and that we will skip that part and just get straight to the differential equations. Does that make sense?
Sure.
Yeah? Okay. So you know the procedure here. I'm just going to go straight into the equations that will describe the behavior of the system, but it's exactly the same as you've been doing so far. Split each mass, create the free body diagram, sum all forces, equate that to their acceleration time mass. You get 2 sets of equations. Okay, I will post in the solutions, I will add the equations here, the procedure to find the equations, but to save some time in the lecture, I'm going to skip that. And this is what we get. These are the 2 equations that we got from doing that. 1 equation for each mass, and you notice here that we ended up with a fourth, with 2 second-order differential equations, which means that if you want to write the system in a state space, we'll need 4 state variables, 2 for each equation. Which ones are these state variables? So let's talk about mass m1, for example. Which state variables can we define for mass m1? We know that we need 4 states. So let's call this x1, x2, x3, and x4. x1, the first state, let's define the first state for mass m1. What would that be? What could that be? Elements that store energy. What can store energy in this system for mass m1?
The spring and the damper.
The damper dissipates energy. It cannot store energy, but the spring does store energy, and it stores energy depending on the position of the mass. So we can define x1 as P of t. That is the position of mass M1. And in the same way, we can define x2 as q of t, which is a position of mass M2, because that will also influence how much energy is stored in the spring. What else can store energy here? Well, each mass can store kinetic energy, and that kinetic energy will depend on the speed of each mass. So what can we say? We can say that x3 is simply p of t dot. Yeah, p of t dot, the speed of mass 1, and x4 is q dot. Now, so x1 and x3 basically are the mass and acceleration of mass 1. Sorry, x1 and x3 are the position and acceleration speed of mass m1. x2 and x4 are the position and speed for mass m2. Our job now is to look for equations for x1 dot, x2 dot, x3 dot, and x4 dot. For x1 and x3 and x2, we'll have to write all the equations to find their derivatives. But for x3 and x4, we can see that if x3 equals to p dot and x1 equals to p, then what is x3? As a function of x1.
X1 dot.
x1 dot. Right. So here is one equation. And same goes for x4. What is x4? As a function of other states.
X2 dot.
x2 dot. Very good. x2 dot. The other ones, you cannot do it because that would require integration. You cannot use integrals, or only using derivatives. So two of the equations are already established. x3 dot equals to x1 dot, and x4 dot equals to x2 dot. What do we do with the other two? Well, now we need to use the equations we established to determine them. So let's take the first equation, equation 1, and rewrite equation 1 as a function of these state variables. So m1 remains m1. What is p double dot as a function of the states? Remember that we always want to go with the lowest derivative possible. So how would you do that for p double dot?
X3 dot.
x3 dot. x3 dot works. Yeah, x3. x3 dot, exactly. So 1 second. Equals to, this is x3 dot. So I just realized here that I made a little mistake in my notation here. We actually established equations for x1 dot and x2 dots, right? So x1 dot is x3 and x2 dot is x4. I just wrote it in the wrong place. Okay, so m1 x3 dot plus b1 times p dot. What is p dot?
X3.
x3. It could be x1 dot, but if you can go with x3 lower, that becomes x3. Plus k1 p. What is p? x1. There's no other choice. Equals to, just check my work here. I don't want to make any mistakes to confuse everybody. So this is equals to u of t. U of t is the input. It needs to stay there. Plus k1 q. What is q?
X2.
x2. Very good. Plus b1 q dot. And what is q dot?
X4.
x4. Excellent. x4. So now we can solve for x3 dot to fill the gap in our table there. So now x3 dot equals to 1 over m1 times u of t minus kx2 minus b1 x4 plus minus b1 x3 minus k1 x4. And this is the equation of our x3 dot. Any questions? No? So if there are no questions, then making the equation for the second mass should be straightforward. So let's try to do that. So m2 is m2, that doesn't change. What is q double dot?
X4 dot.
x4 dot plus k1 plus k2 times q. What is q? x2.
X2.
Excellent. Plus b1 plus b2 times q dot. What is q dot?
X4.
Q dot is x4. Yeah. And this is equal to, my pen is acting, k1 times p, which is x1, plus b1 times p dot, which is x3. Excellent. So now notice that in both of these equations, once we translated them into the state variables, we ended up with only one state having a derivative. If there is more, then you can probably rework the equation there. The idea is to only expose the one derivative at a time in that equation. And that's what we got in equation 1 and 2. Right, you notice that only x4 and x3 have dots. Everything else are simply the states themselves, which is precisely the format we need to write that into the matrix form.
Isn't it meant to be b1 plus b2 x4? You wrote b1 plus b1.
Yes, b2. Yeah, thank you. So x4 dot equals to 1 over m2 times k1 x1 plus b1 x3 minus k1 plus k2 x2 minus b1 plus b2 x4. And that's the last equation we need.
Excuse me, Professor. I have a general question here.
Yeah.
So in this kind of question, how we know that how many variables we need for that, or it depends on like we just find the element that save the energy, and then that means
Yes.
one variable.
So you need as many equations as elements capable of storing energy, which is the same as saying if you have two elements storing energy, you end up with a second order differential equation. So you need two first order differential equations, two states. It's the same statement. If we have a fourth order differential equation, you need 4 first order differential equations and so on, which means that you probably have 4 elements in the system capable of storing energy.
Okay, got it. Thank you.
Any questions here? No? So here are all the elements, well, all the equations we just derived. One for x1 dot, x2 dot, x3 dot, and x4 dot. X3 and x4 should be just dot, not double dot. That's a typo. And you see that they are only functions of the states and the inputs. We can now establish the first matrix. X is our state vector. So that is x1, x2, x3, and x4. Matrix A, if you remember, I have matrix A multiplying x1, x2, x3, and x4 plus matrix B multiplying U of t. And this is equal to x1 dot, x2 dot, x3 dot, x4. So this is A, this is B. What goes in matrix A? For x1 dot, what do we see? X1 dot is only a function of x3, and the coefficient there is 1. So what goes in the line for the first line of matrix A?
0.
0, 0, 1, 0. So if you multiply A by x1, x2, and x3, x3, and x4 vector, we get x3. Let me write this on top here so it's more clear. If you multiply this out, we have 0x1 plus 0x2 plus x3 plus 0x4, which means that x1 dot equals to x3. That's the first equation. There.
I'm sorry, I don't understand like what you do in the matrix. Like, how do you get 0, 0, 1, 0?
So our objective is to multiply out these two matrices to get the equation that I just highlighted, right? So the matrix multiplication would be element-wise like that. So now which elements do we need to put in equation in matrix A so that when you multiply that line with x1, x2, x3, and x4, we get this equation here. The first element, which is x1 dot, is equal to this element times that, plus this element times that, plus this element times this, plus this element times that. If you want to get x1 dot to be only equal to x3, then all elements are 0 but the third one. If there was x3 plus x2, then you would have 0, 1, 1, 0.
Oh, I think I understand now.
Okay, let's try the second line. What is the second line for matrix A? Second
0,
line,
0, 0, 1.
exactly. Second line is coming from the second equation, x2 dot equals to x4. So you only have 0, 0, 0, 1. Now third line, what is the third line? Third line is a bit more complicated. What multiplies x1? Minus k1
or m1.
m1. What multiplies k2?
K1 or m1
K1 m1, kx3.
minus b1 or m1,
Correct. And 4?
b1 or m1.
b1 over m1. And notice that now there is another term that appeared there, which is
B?
u of t. Right. So in the first one here, we had 1, 0, 0, 0, 1, 0, and 0 because there is no u of t, 0 because there is no u of t for these two. But now for x3 dot, we have 1 over m1. Okay, and then the last equation, x4 dot, we have k1 m1 minus k1 minus k2 m2 b1 over m2 and minus b1 minus b2 over m2. And what goes in b? The last line of b?
0.
Why is the first, the bottom left one over M1?
All m2. All m2, sorry. It's all m2. Right, if you look at the equation for x4 dot, is all m2. Okay, are we good here?
Yep.
Yeah. Okay. All right. Now we did half of the job. Now we need to do the other half. And the other half is to now establish an equation for the output. This should just be y, not a y dot. This is a copy and paste. We now want to establish an equation for the output. And the output of the system was chosen to be P of t. So the output is basically x1. Was chosen to be the input, the output displacement of mass m1. So now we need to establish another equation for y of t, which is equal to c times the states plus d times the input, which is u of t. So what goes in these matrices? What goes in matrix C right here? We take that from this equation. This is what you're trying to recreate, remember, is y of t equals to x1. So what goes there?
1, 0, 0, 0.
1, 0, 0, 0. Very good. And then the last one, all zeros, right? Because there is plus 0 times u of t here. That's now the equation for the output. Okay. Any questions? No? All right.
Sorry. Why it is y t equals to x1?
So y of t is the output, and we chose the output to be p of t. And according to the states we defined earlier, p of t is x1.
Oh, okay. Got it. Thank you.
All right, and this is now the complete state space model for the mass spring damper system, which will make it a lot easier to simulate now as a simple set of 4 differential equations rather than a 4th order differential equation. You can now see precisely in this simulation diagram where exactly these signals are. And when we implement that in Simulink, you can simply probe the signal along different points of that model, and then you have access to all of them. Something that would be lost if we had simply input-output relation in the format of a transfer function. All the internal variables are not accessible in the simulation. Well, and this is precisely what we're going to do here. So this is the same exercise we just did. So these are all the equations we used. And now let's go back to the last lecture and derive a block diagram to represent all this. Let's represent all these equations in a block diagram. So you can use this thing here to complete. I'm going to do this in the whiteboard instead. So our job is simple. We have 4 equations, and you want one single block diagram that represents all equations. So based on what we studied in the last lecture, how would you start this? Where would you begin? Where would you begin? What would be the first thing you draw on the diagram?
The input.
The input. And where is the input? That is in the 3rd equation. Yes, u of t is in the 3rd equation. So if it is in the 3rd equation, you're going to start there. What should we do first? We should create the left side of this equation. And the left side of that equation will give us x3 dot. Once you integrate x3 dot, we get x3. And then you can start connecting things. So what we're going to do is first start by creating the left side of the right side, excuse me, of this equation. But you notice that on the right side of this equation, everything is divided by m1. So let's actually multiply both sides of the equation by m1. Comes to this side of the equation, makes it a lot easier. And now we're going to establish this part of the equation in a block diagram, and that will be equal to m1 x3 dots. We then divide it by m1, we get x3 dots, we then integrate to get x3. Okay, so let's get that done. Okay, so here is the block diagram with all stuff in it. Just move my stuff around here. Okay. How do we begin? So we begin with the input. The input is there. If we now take the input, we subtract this, subtract that, we add this, and we add that, we're going to get x3 dot. Right? But again, if we multiply everything by m1, then all these m1s can go for now. And you have here m3, m1, x3, m1. So let's do that. So here's the input. Input is u of s. Yeah, we multiply this by m1, so this m1 will disappear for now. And this will be the output of all the sums. So we are going to feed to this sum all the different elements that we have there. Let me just look at which one I fed first. Okay, so here we have x1 times k1. So if somehow we can get x1 to come in here, we'll find this somewhere else later. And you multiply that by k1. We feed that to a negative sum because of the negative sign. And then you can add that to u. So these will represent now the first two elements. The last two elements. This and that. All right, so we have x1 times, x1 times k1 minus u. So in fact, this element and that element. Now we can add x2 to it times k1. So if you somehow later we'll find this x2 somewhere, and if you take that x2, we multiply that by k1, we can keep adding that in a positive sum. This is positive. This is positive. And then I'll have this term minus that term plus this term. We can continue now with x3. x3 goes here. And x3 is multiplied by negative b1. So b1. And this is a negative sum. Or you could say positive here and then negative b1. I multiply by negative b1 and add a positive number there. That works. Oops. There, this is negative sign over there. And then the last term, so this term is that. And then the last term is x4 times b1. So x4, and you're going to get somewhere, we'll find it later, and x4 times b1 goes in here, and this is a positive sum, so we simply add that there. So positive, and here we have positive 2. Right? Actually, this could go straight there. It didn't even need this sum there. There's nothing going in the sum. It could have gone straight up.
Sorry, where would the I think x3 times b1 is not connected to our actual u of s.
x3 times b1 Yeah, so this connects there.
Oh, okay, thank you.
Right. So now if this is the same as just having a one block here with all these arrows feeding it, right, with the appropriate sign. I'm just putting one, only sums with two elements just to make it easier, but we could feed everything in that one that works. Okay, so this is the left side of this equation. And because we multiplied everything by m1, what is the right, sorry, this is the right side of the equation. What is the left side? This sum, this entire sum is equal to m1 x3 dot. So the output here is m1 x3 dot. This is this signal right there. Does that make sense? If we had here k1 divided by m1, k1 divided by m1, b1 divided by m1, b1 divided by m1, this would simply be x3 dot, right? But we just shifted over there for simplicity. If you now divide this by 1 over m1, what is the output here? This is x3 dot. This is x3 dot. What do we do now? Well, now we can integrate. We can integrate this. And if we integrate, what do we get there?
x3.
X3. And what is x3? X3 isn't x3
x1 dot.
x1 dot, exactly. So this is the same as x1 dot. So what do we do now? Well, we integrate again. And if we integrate again, we get x1. See, now we have x1. We can connect x1 here. We have x3. We can connect x3 there. But we still don't have x2 nor x4. Now we can look at the second equation. This is the first, this equation here, fine? Yeah? No? Maybe?
Sorry, just one more question. U of t and U of s are the same here?
Well, they are the same, but yes, for consistency, let's do U of t. Because we are dealing with integrals and time and dot in a dot in time in frequency domain doesn't mean anything. Right, so yeah, so you're right, this should have been U of t. So let's just now establish the last equation. Let me just look at my diagram and see how I created it. Okay, let's just start it. Let's now do this one. If we do this in part of the equation, we are going to be left with x4 dot. So you see that all these constants are multiplied by 1 over m2. So we can do the same, just multiply both sides of the equation by m2 to make it easier for us. So this will be m2 x2 dot, x4 dot. So if you do the sum with the remaining terms, we get m2 x4 dot. So let's do it here. Let's just start with the first one here. We're going to feed to feed here x1, and you can multiply x1 by k1, and then add that. Start adding stuff up. Here, if we enter x2, what goes in the triangle? So this is x2. We are dealing with the last equation. What goes in the triangle there? What multiplies x2? K1 plus K2. And this is negative. This is positive. Are we good? Or you could write minus k1 minus k2 and a positive sign here. That works too. Just shifting the negative sign over there. Right, pretty much the same place. Okay. So let's do x3 now. x3 is multiplied by b1. So this is b1 times x3. That's b1, and that's positive. So this will feed the sum like that. And this sum will feed the last one. And then the last one is for x4. So x4 is here. And what is inside there? b1 plus b2. Right, and this is a negative sum there, whereas the top one is positive. Okay, so this is this entire summation here. Each of these circles represents one summation. This circle here is useless, it shouldn't even be there. You can just go straight to that one. Same way that this one here is simply performing a negative operation. So the output can keep going now. So what is in the output here? What did we get there?
M2 x dot 4.
M2 x4 dot. So this is M2 x4 dot. So now we need to multiply this by, okay, I'm gonna do here's a multiplication missing. I'm gonna do this. So I'm gonna do multiply here by 1 over M2. So multiply by 1 over M2. This gives us here x4 dot. We take the integral. Now I have to write an integral backwards. Whatever. The integral there. This gives x4. And what is x4?
x2 dot.
x2 dot. Yeah, x2 dot. So let me just try to find. This is not an easy task here. Okay, x4 is the same as x2 dot. See, x2, x4 equals to x2 dot. So this is the same as x2 dot. So now we can integrate one more time. This should have been a triangle here, right? So integrate one more time, and then we have x2. Now what do we do? Oh, now we can connect everything and make a mess. So x2 can be taken from here. x4 can be taken from there. x1 is available over here. It's available over there. And x2 taken from here. Now this is the equivalent simulation diagram. Okay, so notice here that all the states are clearly visible. We have all the x's and everything. So in the case of the mass spring damper system model, we know the input, the output. Where is the output? Where is the output of the system?
At x1.
x1, so here it is. The output is right here. We could write this. It's y of t. That's the output. Input is here. Output is over there. What else we have? We have the speed and position for each mass. We know where they are. I can just probe them there. Okay. Any questions? So why are we doing this? Well, we are doing this to now be able to start simulating these things in Simulink. You see that in Simulink, you have a very similar representation as I shown here. And you'll be able to now input equations in that format, and it's a lot easier to visualize than it is in MATLAB where you just have the differential equations and the transfer functions. So you have a full simulation diagram with all these variables available to you.
What do we
Any
do for
questions?
the, sorry, what do we do for the open X3 terms?
Oh, we didn't connect them. Yeah, so we can, forgot where are they? So X3 is over here. So this X3 can go all the way there. And this X4, I forgot it. Where is X4? There. And this X3 is also, I think, did I forget to connect anything? Of course, this is a bit messy, but the important thing is that all the variables are now available somewhere. We'll find them.
Professor, I
Yep.
just want to ask, will we be asked to draw this kind of diagram in the exam?
Potentially, yeah, not as complex as this, but if I give you this equation, one of these equations, yes, you should be able to derive a diagram for them, yes.
Oh, okay, thank you.
But this is really, if you know how to do the diagram for one equation, you know how to do for any. It just becomes a bit messy because you have multiple equations that are now interconnecting. But other than that, should be fine. Okay, so we have, we're out of time again. Yeah, so I think I'm going to stop here. I don't have time to start a new one. So what I'm going to do is to post the solutions for the remaining exercises. And I think all of them have videos with the full solution you can watch. So exercise 3 is, I think we can skip that one. And then exercise 4 and 5 are pretty good examples. And I'll encourage you to watch them if you have questions. So try exercise 5, you are able to do that on your own. So try that on your own and then watch the solutions if you get stuck. And exercise 4, let me put it up here, it is a bit different because now we are given the block diagram and you want to go back to the differential equation. So let me just give you a quick overview here of what is going on. So you notice that this block diagram has integrators. And if you look at what we just did here, oops. What we just did here, you see that in the output of each integrator, we have a state. That's what the integrators are doing. They're always giving us these states. So it's fair to assume that in this example, we have the same. The output of each of these integrators are a state. So here is what we have. X1 coming out of this integrator and X2 coming out of that integrator. So what is the state immediately before that? If the right side of the equation, we have a state X2, what would be before the integrator? That is simply X2 dot. And if the same goes here, if past the integrator we have a state X1, then before the integrator we have a state X1 dot.
Excuse, Professor.
Yeah.
So in this diagram, actually it is in a frequency domain. So it's a little bit different from what we have that.
No, it is precisely the same thing, except that the integrals are now 1 over s's, but as they represent the integral.
This is what I mean, because one is the time domain, the other one is the frequency domain. For the rest of them, they are exactly the same.
Yeah, so we can write this then to make it more consistent. We can have x2, which in the time domain is x1 dot, which in the time domain is x2 dot. Okay, And now we can rework the equations based on the block diagram itself. I'll just give you one, and then we are gonna let you go. What would be the equation knowing that we have x1 dot right here, if this point here is x1 dot, how can you write an equation for x1 dot there? What is that signal at that point? Isn't that u of t minus x2 times k? x2 past k here is x2 times k. U minus x2 times k equals to x1 dot.